Welcome to my channel. So today we will be discussing about the Rankine cycle, but before we get into the Rankine cycle, let me put up my video. Alright, so what is Rankine cycle? The Rankine cycle is a thermodynamic cycle used in the steam power plants to generate electricity. So this is the main context. You know what? Today approximately 60 to 70% of the world's electricity generation actually comes from thermal power station, that is steam based power plants. So let me again give you another context to let you know how electricity is generated using the steam power plants. Let us start from the boiler. So we have a very big boiler inside which we put the working medium as water. So using coal or some other substances, we can boil the water in the boiler. So once water boils, steam is generated. The steam goes and hits the turbine. The turbine moves. The turbine is connected to the generator. So when the turbine moves, generator also moves. So that generates electricity. So after that, whatever vapor or the steam has hit on the turbine is being collected. So that goes into the condenser where heat exchange takes place, and then the condensation of water vapor to liquid water happens, and that is collected into the tank, and with the help of heat pump, that particular water is put into the boiler once again, and then the cycle actually continues like this. So this is the overall context. So what are the four main components that we have in the Rankine cycle? We have boiler, we have turbine, we have condenser, and we have heat pump. So for the convenience of teaching learning purpose, let me put number 1, 2, 3, 4 in this order. Number 1 between boiler and turbine, number 2 between turbine and condenser, number 3 between condenser and heat pump, and finally number 4 between heat pump and then the boiler. Let me go to the next slide now. You know, there are four main processes that make a Rankine cycle, and these are the most important processes. Once we complete these processes, the basic fundamentals of the working principle of Rankine cycle is over. So the first process is compression. Okay, so this compression happens at constant entropy, so we call it isentropic compression, or it happens in the adiabatic way. That means that to make the process at constant enthalpy, you have to introduce the insulation. By introducing the insulation, you can make the whole process adiabatic in nature. Adiabatic means there is no exchange of heat between the system and then the surrounding. That process is known as adiabatic. So we have compression, heat addition, heat then expansion, and heat rejection. Only four processes: compression, heat addition, expansion, and heat rejection. So compression is at constant entropy. To make it at constant entropy, uh, you have to introduce the insulation. Once you introduce the insulation, that particular component becomes the adiabatic in nature, meaning there is no exchange of heat between the system and then the surrounding. Then comes the heat addition. So heat addition happens at constant pressure. Iso means constant, barik is a pressure. So at constant pressure, heat addition happens. Then we have the expansion. So expansion again, like the compression, happens at constant entropy. So to make the system at constant entropy, it has to be adiabatic in nature. Then finally we have the heat rejection. Like heat addition, the heat rejection has to be also isobaric in nature. So let me put everything in the nutshell. Compression and expansion, they are opposite to each other, and then the conditions are same. They should be at constant entropy and adiabatic in nature. Constant entropy and adiabatic in nature. Heat addition and heat rejection, it should happen at the constant pressure. I'll let you know why it should happen at the constant pressure later on. So once these four processes are completed, then the Rankine cycle is completed. But before we go into the Rankine cycle, understanding about the saturation curve is very, very important, because we are going to begin from the saturation curve. So saturation curve here, saturation curve will be actually understood from two diagrams. One is PV diagram, pressure volume diagram. The other one is TS diagram, temperature entropy diagram. Entropy is represented by S. Okay, so this is the saturation curve. So on the left side of the saturation curve, you have water in the form of liquid. On the right side of the saturation curve, you have water in the form of vapor. Over the top, mostly vapor, but in between you have water in the form of liquid plus water in the form of vapor. Vapor is same as steam. So we are going to begin like that with the saturation curve. So the moment as we are heating the water, the moment the heating process crosses the saturation curve, then the water vaporization takes place, and once it comes out of this one, the water is completely vaporized. And then that is why we call it dry saturated steam. So we are basically going to start from this saturation curve. So let's begin with the first one. Remember, the first one is compression. So I have already informed you, compression has to be adiabatic in nature. At the same time, it has to be at constant entropy. In fact, it has to be constant entropy. To make it constant entropy, you have to design the system in such a way that it is adiabatic in nature. So constant entropy is also called as isentropic. So let's look into this particular diagram. Uh, Out of the four processes, where is the compression happening? The compression is happening in this component, heat pump. The pump is going to compress the water. So the second process is heat addition. Out of these four components, where is the heat addition happening? The boiler is the one where heat is being added. Okay, the boiler is being heated, so heat is added to the water. Okay, so compression, heat addition, and turbine is the place where expansion is happening. Steam is formed, and then steam goes and hits the turbine, and then it gets expanded. So expansion happens on the turbine, and it is the turbine that gives the work done. Okay, after that we have the condenser. So this condenser is simply a heat exchanger, from one side you get the steam, and then here you can run the cold water. So it's kind of a distillation unit. So the steam gets condensed into water, which you can collect it into a tank. Using the feed pump, you can put it back once again. So this is what it is. So the moment we talk about compression, so you should be focusing here, feed pump. So feed pump is between number 3 and number 4. So we can represent it as number 3 to number 4. So here what is happening, the water from the condenser tank is pumped to the boiler with the help of feed pump. So there is a tank here. You can use this feed pump to put the water back into the boiler. So let's look into these processes. What is going to happen here? The fluid that is in the liquid state, here the vapor has condensed into a liquid state. So the fluid is compressed by what? By the pump. So the fluid is compressed while the specific entropy remains the same. So pressure and temperature will rise. See, this feed pump is a closed kind of vessel. It is actually packed with the insulating material. So entropy is going to remain constant in this case, and then pressure and temperature will rise. Let's look into the pressure volume curve. So we are going to begin from 3 to 4, because 3 to 4 is the compression. So 3 to 4. So when you are using the pump to compress the water, so the pressure increases, but you'll see volume will not increase. Why? Because you cannot compress water. You cannot make the water volume shrink by simply using the pump. So therefore volume remains same. Now let us look into temperature entropy diagram. So in the temperature entropy diagram, by simply applying the compression, so the moment you apply the compression, the temperature should increase. So more compression, more molecular collision, so the temperature should increase. Temperature is nothing but the average kinetic energy, so it should increase. But because it is happening at the constant entropy, so the entropy is same. Entropy does not go right or does not go left. Entropy is same. So overall picture, pressure increases, temperature increases, entropy remains same, and volume remains same. Now we have completed the first process of the Rankine cycle, that is compression. let's look into the second process. And remember what I have mentioned, the second process, it is heat addition. So heat addition and heat rejection happens at constant pressure, so we can call it isobaric heat addition. Now if you look at this particular diagram, it is the boiler where heat addition happens, and boiler is between number 4 and number 1, so therefore we can call it as 4 to 1 process. So let us see what is going to happen, right? So the water is heated up to saturation temperature. That means we will have to look from this 4 to number 1 process, right? So 4 to 4 dash. During 4 to 4 dash, when you are applying heat in the boiler, slowly the temperature reaches to the saturation temperature of the water. So 4 to 4 dash. Now after this, depending upon how much heat we supply to the boiler, it can either form the wet steam, that is represented as 1 dash, or you can have dry saturated steam, that is represented as 1, or if you are supplying extra amount of heat, you can also have superheated steam, that is represented as 1 dash dash. So remember what I have mentioned already, inside this bell-shaped curve is in the mixture of liquid and vapor. So that is why this 1 dash is a wet steam, and then this 1 is a dry steam, and then 1 dash dash is superheated steam. So this is what is going to happen here. So inducing vaporization of fluid in the boiler involves heating the fluid under constant pressure, resulting in the phase transition from liquid to a mixture of liquid and vapor, or to a dry saturated steam. The pressure remains constant throughout the process. The phase changes from liquid to gas, and then this changes involves the absorption of latent heat, which I'm going to talk about shortly. So here you can see that it is happening at constant pressure. The question is, why constant pressure? Pressure remains constant during the heat addition process because the boiler is a closed vessel, first of all. Secondly, pressure must be constant in the heat addition process because any change in pressure will result in change in boiling point of the water. And if the boiling point of the water changes, it is going to disturb the uniform flow of the steam into the turbine. The steam is flowing into the turbine, right? So sometime if the boiling point reaches faster, so we have a more amount of steam coming in, sometime less amount of steam coming in, until and unless we maintain the constant pressure. If that happens, the turbine can be damaged, and whatever electricity being generated, the voltage fluctuate. So we must make sure to design the design the engine in such a way that the pressure remains constant. So this is one of the reasons as to why pressure has to be constant. Now let's look into the PV diagram of isobaric heat addition process. So when you are adding heat, because it is happening at the constant pressure, so there is no change in pressure, first of all. So the moment you start adding heat, the volume increases. Initially, whatever volume occupied by the liquid starts getting expanded the moment it starts forming the vapor. So therefore, you can see volume being increased towards the right side. Okay, so pressure is constant and volume changes. That means volume increases. Now let's look into the TS diagram. So 4 to 4 dash, 4 dash to 1 dash, 1 dash to 1 and 1. So in all the way from 4 to 1 dash dash, especially from 4 to 4 dash, there is a rise in temperature. Why? Because the moment you start giving the heat to the water through the boiler, then the temperature rises. But here is an interesting thing. The moment it reaches the saturation curve, then once it comes until it comes out of the saturation curve, so you'll see a constant temperature. The temperature remains constant. Now the question is, why does the temperature remain constant? So during the latent heat of vaporization, this process is nothing but latent heat of vaporization is happening. The temperature doesn't increase because all the heat supplied is used to break the intermolecular bonds between liquid molecules so that liquid changes to vapor phase. The supplied heat is not to increase their kinetic energy. It is actually used to break the intermolecular bonds so that liquid phase of the matter is changed to vapor phase. So that's why we don't see the increase in the temperature. But here you see there is a sharp rise in the temperature that happens when once all the water is evaporated. After that, whatever heat supplied through the boiler can rise the temperature. So this is it. So overall pressure remains same, temperature remains same during the latent heat of vaporization stage. Entropy increases, which I have shown you here. So overall entropy increases the moment you start supplying extra amount of heat through the boiler. Intermolecular collision increases, so therefore the entropy increases. Entropy simply means the randomness, and volume also increases the moment we supply heat to the system. Now we have completed the second process of the Rankine cycle. The first process was a compression, and second process is heat addition. And what is going to be the third process? The third process is expansion. That means once you have compressed, you have supplied the heat. Once you have supplied the heat, then there is going to be expansion. So expansion is going to happen here. Now let's look into the third process now. So this is the third process. Uh, so this process where expansion happens is in the turbine. So therefore the turbine is between number 1 and number 2. So here what is going to happen? The steam enters into the turbine where it expands at constant entropy, and it enters into the condenser pressure. After that it enters into the condenser pressure. So I told you already that compression and expansion happens at constant entropy, and to maintain constant entropy we have to make sure the design has to be adiabatic in nature so that heat exchange does not take place. So that's why we also call it reversible adiabatic expansion or isentropic expansion. So here the fluid expands through a turbine while maintaining the constant entropy. So now let's look into the PV diagram. So in the PV diagram, the expansion is happening here. 1 dash to 2 dash, 1 to 2, 1 dash dash to 2 dash dash. So whenever expansion happens, the volume increases. So you can see here the volume is increasing for all these three different states of the matter here. Volume increases. So when volume increases, the pressure decreases. So you can see increase in the volume, decrease in the pressure in the PV diagram. Now let's look into the TS diagram. So what happens when there is an expansion? And remember, this is an adiabatic expansion. Adiabatic expansion happens at constant entropy. So entropy does not change. So you will see a straight line falling down from all these three different states. Straight line, because entropy does not change. But here you can see the overall temperature changes. Whenever expansion happens, the temperature decreases. So what happens is that when expansion happens in the context of thermodynamics, work is done by the system on the surrounding at its own at the expense of its own internal energy. So therefore the system loses the internal energy which is related to the heat, and that you can measure it using temperature. So temperature drops whenever expansion happening, or whenever expansion happens the temperature drops. So this is what is going to happen. So here you will see the volume increases, pressure decreases, temperature decreases, and entropy remain same. So now we are coming to the last process of the Rankine cycle. So please remember what should be the last process of the Rankine cycle. We started with the compression. So compression followed by heat addition, followed by expansion, and then the last process is going to be the heat rejection. This is the last process, heat rejection. So in this diagram, where is the heat rejection happening? So this is the place where heat rejection happens. Heat rejection happens at condenser. So that means it happens between point number 2 and point number 3. The exhausted steam, we can use the word exhausted because it has already moved the turbine. So the exhausted steam is condensed completely into the condenser, and then once it forms the water, once the vapor changes into water, you can collect it into the tank. Now once you do this one, the cycle completes. After that we can use the feed pump and put this water once again into the boiler. So the cycle is completing here. Okay, so okay, that is the case. So here if you want to see what is happening, inducing liquefaction of the fluid, that is water, involves the cooling the fluid under constant pressure, causing the vapor to condense. So once again let me remind you that heat addition and heat rejection happens at constant pressure. I told you already, especially for Rankine cycle. So a significant decrease in the entropy is also observed during the process. Now let's look into the PV diagram and then followed by the TS diagram. So first of all, let us look into the PV diagram, pressure volume diagram. So now whenever condensation happens, the vapor condenses back into liquid. So initially the vapor was occupying a major space. So when it becomes the liquid, the volume decreases. So therefore you can see 2 dash or 2 dash dash drastically decreasing the volume. But here, because it is happening at the constant pressure, the you will not see there is a increase or decrease in the pressure, because it is happening at the constant pressure. Let me tell you why it has to be at constant pressure. If it is not at the constant pressure, the rate of the condensation is going to be different. Sometimes more water is condensed, sometimes less water is condensed. So if that happens, sometimes the feed pump will have enough water to pump to the boiler, sometimes the feed pump will not have sufficient water to put to the boiler. What we want is the uniform flow of the water. So to maintain the uniform flow of the water, the pressure has to be constant. Now let's look into the PV diagram and then followed by the TS diagram. So PV diagram is completed. Let's look into the TS diagram. So here, when the condensation happens, you see, be it 2 dash or 2 dash dash, you can see that temperature does not change. The temperature is stable. Remember, in the heat addition process also, once vaporization started, the temperature was constant. Now also the temperature is constant. Do you know why? Do you know why temperature is constant? So let me give you the answer for this one. So during condensation, the water vapor releases its latent heat during the phase change from vapor to liquid. Condensation means vapor is converted into liquid one. So when that happens, latent heat is released. Now, if that is the case, is it released outside? We have to understand this one. This latent heat is then used by the system to form the intermolecular bonds between the water molecules. Remember, when water was forming the vapor phase, the intermolecular bonds was broken and then heat energy was required. So heat energy was used to break the intermolecular bonds. Just now the heat energy is released, latent heat is released, and then the same amount of latent heat is used to bring together the vapor molecules and condense them into water. So therefore we don't see change in the temperature. So finally the temperature is same, but then because the vapor is condensed into liquid, so vapor means more number of more freedom for the water vapor molecules to go and collide and then cause the randomness. But then liquid means that actually decreases, so therefore you see change or decrease in the entropy. With this we complete the Rankine cycle, but we have also the last one to actually calculate the efficiency of Rankine cycle. How do we calculate the efficiency of Rankine cycle? So here, if you look into this once again, this loop diagram, you have 4 components starting from the feed pump to boiler to turbine and then finally your condenser. There is a work done given to the system by the pump. When we are using the pump, we're using the pump to actually pump the water from the tank and put it in the boiler, right? So this particular work done is represented as WP, W for work, P for pump. And this is the work done given by us to the system. And then here boiler. So here heat is provided to the boiler, right? So heat is represented by Q, B for boiler. So we give heat energy to the boiler. And then turbine. So here turbine, this is the place where actual work done happens, right? And this is what we want finally. So the turbine moves, generating electricity, which is connected to the generator, right? So here the work done given by the turbine is represented by wt, w for work done, t for turbine. And finally, condensation happens at condenser. We can represent qc. Q means heat, c means at condenser. This is given off, the heat is actually given off. Now let's look, finally our aim is to calculate the efficiency of the Rankine cycle. So let's look into WP. We are starting from here, work done provided by the pump. Now pump is between number 3 and number 4. So it is the enthalpy difference between 3 and 4. So you have to actually tell me where is more enthalpy. So we have more enthalpy here. Why? Because the pump has compressed the water and then enthalpy has increased. So therefore it is HF4, F for fluid. Okay, so HF4 minus HF3. Then QB, so QB is located between 4 and 1, but it is the enthalpy difference between 1 and 2. Why? Because this enthalpy 1 is more than enthalpy 4, because here you have supplied heat. So that is why it is H1 minus HF4. Then WT. So in WT, it is the enthalpy difference between number 1 and number 2. So here, after the work done, the enthalpy is less here. But this is before the work done, there is a maximum enthalpy here. So therefore, it is the enthalpy difference between H1 minus H2. And finally, we are coming to the QC, that is heat rejected by the condenser. So this condenser is between 2 and 3. So this is the enthalpy difference between 2 and 3. Now you'll have to see where is more enthalpy change or where is more enthalpy. So once condensation happens, heat is lost. So number 3 has less enthalpy. So this is going to be H2 minus HF3, F for fluid. Now what is the net work done? So I told you already that we also provide some work done to the feed, but the actual work done is done by the turbine. So the net work done by the Rankine cycle is Wt minus Wp. So this what is the efficiency? This is eta. Okay, so what is the efficiency of Rankine cycle? It is output minus input. Output is nothing but the net work done. Input is the Q amount of heat supplied to the boiler. So W net by QB. So what is W net? Net is Wt minus Wp, and here we have QB. So if you expand everything, then what you are going to get? Wt is here, right? So Wt is nothing, H1 minus H2. You can put it in the bracket. After that, minus Wp. Wp is here. So Wp is HF4 minus H3. You can put it inside the bracket. Divide by, you have QB. QB is here. So it is H1 minus HF4. In many textbook, work done provided by the feed pump is negligible as compared to the work done generated by the turbine. So they take it as a negligible. Even don't take it, but it is good if you want to maintain the accuracy. You want to consider this one. So if we know the data from the steam power plants about all these enthalpy changes, we shall be able to actually calculate the efficiency of the Rankine cycle. So this is the overall picture. So thank you so much. I hope you like my video, and then if you want me to uh, you know uh, make more videos on science related areas, please let me know through the comment, and thank you so much.